Good evening. Welcome back to this series of lectures on quantum mechanics. All right. This is our second lecture, and we will be discussing a few of the topics, including how we calculate probabilities theoretically, what we mean by a wave function. We are all familiar with the word wave function. Okay. And another important concept called inner product, orthonormal basis, Hermitian operator, all these things. Okay. All right. So what we did in the last class was, we started with the double slit experiment. Okay, we started with the double slit experiment. Right. So this was supposed to be, this is a thought experiment, all right, and this was supposed to be a quick way, right, a quick way to introduce the mathematical framework, all right. So and then from this double slit experiment, we motivated that there is something in nature called as the superposition principle. We have got something called as the superposition principle. So we have got the double slit experiment. We introduced it as a quick way to get to the principle of superposition, right? How it actually exists in nature. All right, and from this we motivated the idea that linear vector space, the vectors in linear vector space behave like quantum mechanical states. It obeys the principle of superposition in that sense. All right, so it was not a really rigorous logical argument, but we quickly reached the mathematical framework. All right, and in the mathematical framework, we saw that there was a nice correspondence between nature on the one hand. All right, nature on the one hand, and the mathematics or mathematical world on the other hand. Okay, all right. So, and the reason why we believe in this mathematical framework is because it works. All right, that's the final motivation for it. It's not a proof. It's not this is not a proven thing or anything like in mathematics, but we know that this works. Okay, this works. That's why we choose this as the correct description of quantum mechanical world. Right? So this was the correspondence that we talked about. We have got quantum mechanical states which are described by vectors or represented by vectors in Hilbert space. Hilbert space was the state space. Hilbert space was the state space, okay, of quantum mechanical states. Right? In classical mechanics, it was phase space. Here it's a state space. Right. And quantum mechanical observables are Hermitian operators, represented by Hermitian operators. We said that Hermitian operators are those operators whose eigenvalues are real. Eigenvalues are real. Okay. And the eigenvalues are the measured values. So if you want to know, or if you want to know if you want to predict the measured value, for example, of energy, you just have to take the corresponding operator and see if we can calculate the eigenvalue of that operator. That would be the measured value. Okay, or measured values generally are eigenvalues. Okay, and I also mentioned that this is a different kind of logic. Right, it's not classical mechanics is a kind of logical framework. We call it as a paradigm. Okay, and quantum mechanics is a different paradigm. It's a different set of rules. It's a different set of rules. Okay, quantum mechanics is an entirely different set of rules. It has an entirely different underlying logic. It has an entirely different set of logic. So the first thing when we go to quantum mechanics is to get used to this new kind of logic. Right. So before going into quantum mechanics, maybe in your undergraduate years, we are familiar with the Newtonian kind of thing. We study F equal to ma. We try to solve these equations. We know that particles have definite trajectories, definite states, etc. Okay, and once we go into quantum mechanics, the main challenge is to get used to this different kind of logic. Right, so we need to slightly reorient our minds. That's the key to understanding quantum mechanics, or the key to following quantum mechanics, or doing problems in quantum mechanics. Okay. So with that introduction, I think we can go to today's portions. Okay. All right. So these Hermitian operators, we haven't gone deeper into this Hermitian operator. We haven't really explained what a Hermitian operator means. Okay, we haven't really explained what Hermitian operator means. We'll come to that. Okay, before that, I need to give you a quick glance into this. We have a very short amount of time. Okay, we have a few lectures in this series. So I just want to give you a bird's eye view first to get a conceptual clarity. Okay, so Hermitian operator, we said that for a matrix, if the operator is represented by a matrix, all right, then the Hermitian matrix is Hermitian if A is equal to A dagger. And how do you get dagger? You first complex conjugate all the elements and then also take the transpose. Right? That's what we mean by a Hermitian operator. All right. We'll see. We'll look into it a bit more deeply because Hermitian operators are really absolutely important in quantum mechanics. It's really fundamental. Okay. And Hermitian operators have a nice property. Okay, I'll just give it here. I want you to just keep it in mind that Hermitian operators have this nice property that will make it more rigorous as we go on into the course. All right. So Hermitian operators have this nice property that they are one property is that eigenvalues are real, and another is that the eigenvectors of a Hermitian operator form a basis. Okay, this is a very important property of Hermitian operator, and this fact is really fundamental to quantum mechanics. Okay. Right, eigenvectors of Hermitian operators form a basis. What do we mean by a basis? We'll make this more rigorous. All right, I'm just giving a glance into these things. Right. So what do we mean by a basis? By basis we mean, for example, if you have a vector in three-dimensional Euclidean space, we need a hyphen here. So if it's similar to a three-dimensional Euclidean space where any vector is expanded in terms of some basis xi plus yj plus zk. All right. This set I, j, k is known as the basis. Okay. What do we mean when we say that this is the basis? We mean that any vector, the important point about basis is that any vector in this space which live in the space can be written as a combination, right, as a sum combination of the basis vectors. Okay, that's the importance of basis vector. Choice of basis is not unique, right? You could choose ijk or something else. It's not really unique. Okay. All right. So this is basis. This means that any vector, a vector. This is in three-dimensional vector space. I'm just giving it to you as an example so that you can understand. Okay. So a vector, any other vector, a vector can be written as, let's say, axi plus ayj plus azk. Right. And sometimes, most of the times, we write only these components of this vector. Right. This ax, ay and az are known as the components of a vector in the basis ijk. Okay. So this ax, ay and az, these are known as the components of vector A in the basis, okay, or in a particular coordinate system I, j, k. Okay, this is this, and usually we write this as a column matrix. Okay. Usually we write simply this as a column matrix. A vector can simply be written as a column matrix ax, ay, az. Okay, I hope you are familiar with these things. We don't have to mention the basis. We can always work with the components alone. We can always work with the components alone. The same thing we'll be doing also in quantum mechanics. So the idea of the basis is the same thing. It's a complete set of vectors. Okay, so here these are complete set of linearly independent vectors, so to speak, because in three-dimensional space you can have only three independent vectors, not more than that. Okay, you can choose one direction, you can choose one direction perpendicular to it, and you can choose one more direction which is perpendicular to both these directions. All right, so if it's perpendicular, it means they are linearly independent. They are independent. Okay, so this basis here, it's a set of maximum number of, by basis we mean it's a set of the maximum number of linearly independent vectors. Alright, and in three-dimensional space the maximum number of linearly independent vectors is 3. Okay? If you consider a fourth vector, you can always express it in terms of these three basis vectors. Okay, that's the idea of that's what we mean by linear independence. Okay. So what we see here, what I wanted to say is that in a similar manner, Hilbert space is infinite dimensional. It's not a real space, etc. It's a vector space. Okay, it can be infinite dimensional. It need not be infinite dimensional. All right. So the idea that we are getting from here is that the vectors, the eigenvectors of Hermitian operators form a basis. Okay, this is important. We'll come back to this. All right, but I want you to understand what we mean by this. This means that any vector can be expanded using the eigenvectors of a Hermitian operator. Okay, if you take a Hermitian operator, you know the set of eigenvectors. You can expand any vector in that space as a linear combination, as a linear superposition, as a linear combination of the eigenvectors. Okay, all right. Now, with that, let me go to an example. Let's try to understand the rest of it through an example. All right. So you can imagine this is a problem. Let's do a small problem. Okay, this is the problem. The vector representing the state vector, or the vector in linear vector space representing a system is an eigenstate of the energy operator. Okay, so we said that corresponding to every observable there is a Hermitian operator, and the Hermitian operator corresponding to energy is often called as the Hermitian operator. Okay, Hamiltonian operator. I'm sorry, it's a Hermitian operator. It's called the Hamiltonian operator. Okay, so for now, for our purposes, Hamiltonian operator is the Hermitian operator. Representing the observable known as energy. Okay, all right. Okay, so the given, so the question, what's given in the question is this: the vector representing a system is an eigenstate of the energy operator, right? So we have got a vector. They say that this is the vector that represents your system. This is the vector in Hilbert space that represents your system, and it's also given that it's an eigenstate, it's an eigenvector of the Hamiltonian operator. Okay, by H hat we mean it's the Hamiltonian operator. Right. So when we say that this is an eigenvector of the Hamiltonian operator, we mean that an eigenvalue equation exists like this, where this E, we can write as E0 if you like. This is just a value of energy. This is just a real number. Okay, this is just a real number. So in this case, we have got a simple problem. We are given a state vector. It's said that it's an eigenvector of the Hamiltonian operator. And what is if you measure the energy of this state, or if you measure the energy of the system represented by this vector, what would you get? What answer would you get? Right? And we go back to our postulates, or we go back to our correspondence. We said that the measured values are eigenvalues. Okay, so obviously the answer here would be E0. Okay, E0. So the answer here is E0. Right? Because psi, this ket psi, we call this as a ket. Okay, the ket psi is an eigenvector, or it's an eigenvector of the Hamiltonian corresponding to the eigenvalue E0. So if you measure the energy of this state, okay, you will get E0. Whatever this eigenvalue is, this is a real number. That's the answer that you will get. All right. So this part is simple, no problem there. Okay. Now the question is, what if the given state is not an eigenstate of the Hamiltonian? All right. So what if the given state is not an eigenstate of the Hamiltonian? Then what does quantum mechanics say about the measured value of energy? I hope the question is clear. The question is this. Okay. So we have already seen that if this vector, if the given vector is an eigenvector of the Hamiltonian, then the measured energy, if you measure the energy of that system, the measured energy value would be the corresponding eigenvalue. No problem there. Okay. The question is this: if the given state psi is not an eigenvector of the Hamiltonian, what does quantum mechanics say about the energy value that you may measure? You try to measure the energy of the system. What's the energy of the system? Okay. So to see this, what we do is that now here psi, all right, we'll call this psi, is not an eigenstate or eigenvector of Hamiltonian. Okay. Now what do? Now we use the idea that the eigenvectors, we have got a set of eigenvectors of H cap form a complete set. Right? I just mentioned this property, a complete set, or it forms a basis. All right? We don't go into the details of what kind forms a basis, a complete set of basis vectors. All right? A complete set of basis vectors. We know this, right? We know this property of Hermitian operators. Hamiltonian is a Hermitian operator. Okay, so the given state is not an eigenvector of the Hamiltonian. So what we can do is that we'll take the eigenvectors of the Hamiltonian. There are a set of eigenvectors of the Hamiltonian. Right? We are not going into the subtleties introduced by degeneracy, etc. We'll come to that. Okay, we'll keep it as simple, assuming there is no degeneracy. If you don't know what's degeneracy, don't worry. Right? This is the simplest case that we are talking about. Okay. Now suppose now what we do is that let phi I be the eigenvectors, okay, eigenvectors or eigenstates of H. Okay. This means that all the phi I satisfy this relation is equal to Ei phi I. Right? All these vectors are eigenvectors of the Hamiltonian operator. Okay. Now we use the fact that these eigenvectors form a basis, which means that any vector, okay, the vector given here, any vector can be expanded. Okay. As a combination, we will write a summation over I, Ci phi I. Okay. This means that we are multiplying it by some scalar quantities, C1 phi 1 plus C2 phi 2 plus C3 phi 3 plus etc. Okay. And depending on the dimensionality of this. Suppose there are only 3. We can imagine there are only 3. Okay. 3 possible energy values. Okay. I hope this is clear. All right. So if psi is not an eigenvector of the Hamiltonian, what you do is that you expand this psi in terms of the eigenvectors of the Hamiltonian. That's what I have done here. All right. Now is the important part. Okay. Quantum mechanics says that the probability, quantum mechanics now says that the probability, okay, I'll write it here, probability of measuring energy EI, okay, measuring energy EI is proportional to these expansion coefficients. Okay, it's proportional to this, sorry, the modulus square of these expansion coefficients. All right, this is one of the other things that we missed last day. All right, I said that quantum mechanics also must take into account, or quantum mechanics also must predict the probabilities of measurement. Okay, for example, we talked about the electron being in 2 slits at the same time, but when we make a measurement, 50% of the times we see it in slit 1 and 50% of time we see it in slit 2. Right? And suppose the experimentally measured probability is 50%, quantum mechanics has to predict this. And how does quantum mechanics predict? It says that the probability for measuring a particular value is proportional to the expansion coefficient, all right, corresponding to that particular value. All right, so I'll make it all a bit more clear now. Okay. So I'll write it like this. P, all right, so we can, what we did is that psi is equal to, let's say there are only 3 states, okay, C1 phi 1 plus C2 phi 2 plus C3 phi 3, okay. Now you are asking, what's the probability that you measure energy E1, all right, what's the probability to measure energy E1, okay. Then you look at the expansion coefficient of the corresponding eigenvector. We have expanded the state in terms of these eigenvectors, right? If you are asked the question, what's the probability of measuring E1, you look at the expansion coefficient of the corresponding eigenvector, and quantum mechanics says that the probability of measuring E1, okay, the probability of measuring E1 is proportional to modulus square of that particular expansion coefficient, okay? It's a proportionality, right? Why do we say it's a proportionality? If these are probabilities, then the total probability has to be 1. If there are only 3 possible energy values, when you make a measurement of energy, you should get one of these possible energy values, all right? Otherwise, our theory is wrong. So this means that they have to be normalized. The total probability has to be equal to 1 plus modulus C3 square is equal to 1. This is normalized. Okay. Now, if this is not equal to 1, suppose it's A, then you can normalize it by taking C1. Instead of C1, what you will write is C1 divided by square root of A, or instead of modulus of C1 square, what you will write is modulus of C1 square divided by A. Okay. Then this will be normalized. All right. Okay. So this part is the normalization part. If summation over I Ci square, this means modulus C1 square plus modulus C2 square plus modulus C3 square in our case. Okay. If this is equal to 1, then this part is 1. If this is not equal to 1, you have to divide by it, so that the total probability becomes 1. This is known as normalization. Okay. In problems, we may have to normalize them. Okay. Okay. So the final thing that I want to give here is that, what does quantum mechanics say about the probability of measuring a specific energy value? Let's say EI, I'll write it like this. P of measuring EI, the probability of measuring EI is equal to modulus of Ci square. What is this Ci? It's the coefficient of the eigenvector corresponding to the energy EI. What is Ci? It's the coefficient of the eigenvector corresponding to energy eigenvalue EI. All right. It's so in this expansion. Okay. So quantum mechanics says this is the probability. I hope that's clear. The probability. This is one important thing that you have to keep in mind. All right. And there's one other thing. There are many other things, but there's one other thing. What happens after a measurement? There's the question of what happens after a measurement. Okay. All right. So this is our state. Let's say the given state we expanded in terms of the eigenvectors of the Hamiltonian operator. All right. So we write C1 phi 1 plus C2 phi 2 plus C3 phi 3. Right. For a moment, let's assume that it's normalized. Okay. Let's not worry about normalization, but let's assume that the modulus square, if you add the modulus square, it's equal to 1. So in order to get the probability, you just find modulus of Ci square. All right. Now the first question is, what's the probability of measuring energy value E2? The probability of measuring energy value E2 is equal to modulus C2 square. What do we mean by modulus C2 square? You take the complex conjugate and multiply by it. Okay, that's a modulus square. All right. So this is the probability of measuring energy value E2. Now after you make a measurement, all right, as I said, this state is in a superposition of all these three energy states. Right. This state is in a superposition of all these three energy states, or in our language, in the language that we chose from the beginning, we can say that if this is the state, then the electron, let's say this is the state of an electron, all right, the electron exists, okay, in all three energy levels, energies at the same time. Okay, so we are saying that E1, E2, E3 are the possible values of energy. All right, and what's the energy of the electron here? The electron is actually existing in all these energy values at the same time. Electron has all these energy values at the same time. In other words, the electron exists in all these energy states at the same time. Okay, that's what we understand from this state. All right, but when you make a measurement, you never observe the electron in superposition. You never measure the electron being in different energy levels at the same time. You never measure the electron being in two slits at the same time. We always measure it in one slit. We always measure it in one energy level. All right. So suppose the measured value is energy E2. Okay, energy E2, and after the measurement, the state of the electron changes. Okay, initially the state was psi. If you measure the energy E2, the state of the system changes to phi 2. Right? It's like we said, it was we said in the double slit experiment, we said that the electron is in slit 1 and slit 2 at the same time. Once you make the measurement, you either see it in slit 1 or in slit 2, never both. Right? So after the measurement, let's say that we got it in slit 1. Right? So then we say that after the measurement, now the electron is only in slit 1, not in slit 2. Okay. Now this is the after measurement state of the electron. So the measurement actually changes the state of the system. The measurement actually changes the state of the system. Okay. So this is what is going on in quantum mechanics. Okay. So I'll try to explain this once again. Okay. So this might be a bit too much to take in at the moment. I'll just explain it once more. All right. So what we do is that we expand the given state vector in terms of the eigenvectors. All right. Ci phi I. Right? And the probability, let's assume it's normalized for the moment. The probability of measuring energy value EI is given by modulus Ci square. Fine. And what happens after measurement? After measurement, the state of the system, the wave function or the state of the system, the vector reduces from psi to one of these states. Okay, after measurement, suppose you measure energy EI, the state becomes the state of the system is phi I. Okay, not in all these states, but in this one state. Now what happens if you measure the energy again of this state? What happens if you again measure the energy of this state? Alright, then you will again get EI. Suppose this is phi 1, for example. Alright, suppose this is phi 1. Okay, now the new state of the system is phi 1, and we know that it's an eigenvector of the Hamiltonian corresponding to eigenvalue E1. Now if you now measure the energy of this system, you will always get E1, just like in the previous case. Alright, so if it's in an eigenvector, if you measure the energy, you will always get the corresponding eigenvalue with probability 1, with probability 1. Okay, so after the measurement, the state has reduced to phi 1. Okay, and now again after one measurement, you measure it again. If you measure the energy again, if you choose to measure the energy again, you will always get E1 with probability 1. All right. Okay, so this is actually the basic framework of quantum mechanics. What quantum mechanics predicts is probabilities for measurement, not exactly what value you will get, but probabilities. And these probabilities can be experimentally tested, and they are very accurate. All right, as I said earlier, it all works well. All right, so this is the what do you say? These are the rules of the game. These are the rules of the game. Now you may often ask, what does all this mean about the electron being in different energy states at the same time? What does all this mean? Okay. And then some professor might tell you, all right, you know the rules of the game, just play the game, don't ask unnecessary questions. Okay, so that's known as basically Copenhagen interpretation. You just shut up and calculate. You know how to calculate the probabilities. What more do you need? You calculate the probabilities, they are correct, it works, it's all perfect, fine. All right, but a few people do ask, okay, what does all this mean? And still it's an open question. All right, nobody knows exactly what all this means. There are certain ideas, there are certain very interesting ideas as to what all this means about the subatomic world or about our universe in general, but there is no consensus. We don't know exactly what is going on. Okay, now I hope that's clear now. Right. I think I have covered all these things. Okay. Now let's discuss what we mean by the wave function. Right. Wave function is usually used nowadays. It's used generally to describe any state. Okay, just to mention any state. Or it's used interchangeably. It's nowadays used interchangeably. Okay, with state vector. Okay, so if we are given a state vector is given like this, we say that this is the wave function of the system. It's used like that nowadays. All right, but historically, initially, the idea of wave function was some complex function psi of x. Okay, now I want to tell you what this psi of x means in our linear vector space formulation. All right, or in our Hilbert space formulation. So, for example, if you started studying quantum mechanics in your undergraduate years, the only thing that you deal with is the psi of x, some complex function. Okay, there is an equation obeyed by this complex function. It's known as the Schrodinger equation, etc. You might have seen all these things. Okay. All right. Now, what's the place of this psi of x in our what's the place of this psi of x, this wave function, in our linear vector space formulation? That's the question. Okay. The idea is this. We said that eigenvectors of Hermitian operators form bases. All right, and we know that all observables corresponding to all observables, you have a Hermitian operator. Okay, we said this. All right. So we see that the basis is not unique. You can choose the eigenvectors of the Hamiltonian to express the state. Okay, the same state. You can use the the eigenvectors of the momentum operator. You can use the eigenvectors of the position operator. We call it as x cap. Okay, so we'll represent the eigenvectors of momentum operator like that. We'll represent the eigenvectors of the Hamiltonian operator like that. Okay, of the momentum operator, we'll just write it inside. All right, we can represent the eigenvectors using the eigenvalues inside the angled bracket. Right? We said you can consider that vector. We can represent the vector like that, or we can represent. Alright, you can write the eigenvalues of position operator. Eigenvalues of position operator are positions. Alright, you can write it inside the angled bracket. Alright. Now, what happens if you expand the given vector if you expand the given vector in terms of the eigenvectors of the position operator. All right, what happens if you expand the state vector, all right, or what do you say, the state vector, yeah, of the vector in Hilbert space, all right, in terms of the eigenvectors of the position operator. All right, so we said that this state, if these are discrete, in this case we said that it's summation over I ci phi I, and we said that this modulus of ci square is associated with the probability of measuring energies. All right, hereafter I'll assume that these are normalized. Okay, so we said this. Now what happens if we have position eigenvectors instead of energy eigenvectors? So energy eigenvectors of the Hamiltonian operator. What if we have position eigenvectors? In that case, all right, corresponding to each position you will have an eigenvector. In other words, it's continuous. Okay, these are continuous. The case that we discussed earlier, these were discrete. Okay, there were a few discrete energy levels. In this case, they are continuous because every position, every point you can think of is a possible position eigenvector. All right, or it's a possible position of the electron. Right? So if you expand it, instead of the summation here, you will have an integration. Okay, and instead of expansion coefficient here, corresponding to every position, you will have a complex number. All right. All right, corresponding to every position, you will have a complex complex number. Okay, so that's why we write it as a function. What does the psi of x give you? The psi of x says it gives you, or it spits out a complex number for any value of x that you put in, any value of x. All right, so you put in the value of x, this function will give you a complex number, and these complex numbers are the expansion coefficients. Since these are continuous, instead of the summation here, you will have an integration over dx. All right, and as I said earlier, we said that we can represent the vectors by their expansion coefficients alone. So we can represent the state by their expansion coefficients alone, and this is known as this was the initial wave function that Schrodinger used. Okay. So this is the place of the wave function in our linear vector space formalism, or in Dirac formalism. All right. What are these? These are just the expansion coefficients corresponding to position eigenvectors when you expand the given state. All right. Similarly, you can do that for momentum also. All right. So you can expand it in terms of momentum eigenvectors also. Again, momentum is continuous. Usually, if you take a free particle, it's continuous. All right. So you see that there is an integration over dp. Instead of a summation over I, you will have an integration dp, and the corresponding wave function, it's also known as the momentum space wave function. Right, the momentum space wave function. All right, or we can say it's a momentum representation of the wave function. And this is the wave function that usually we start studying in, let's say, in our undergraduate years. Right, so I wanted you to make this connection between the linear vector space formalism and these numbers. Initially, it's a bit confusing, all right? Initially, it's a bit confusing because we write psi here inside a ket and we write psi of x here, so it's all a bit confusing. And sometimes we call this quantitative wave function also. Right? So it's all a bit confusing, but you have to keep in your mind that these actual wave functions that we started talking about, or Schrodinger started talking about, are these expansion coefficients of this state vector in the position basis, all right? In the basis formed by the position eigenvectors. Okay, so again, it's all a lot to take in, but we have a short period of time, and we'll try to cover at least the conceptual framework of quantum mechanics. All right, that's a lot at the moment, but I think you can follow. Right, you can think about it. So it's nothing really much to understand here. All right, it's not really much to understand here as such, but what you need to know is that I'm giving you the rules of the games, and you have to remember them. Rules have to be remembered, that's all. And you will get used to it, all right? If you do a few problems, you will easily get used to this. If you do a few problems, you do some practice, you read a few books, and then you will easily get used to this kind of thinking. And then quantum mechanics is as easy as any other subject in physics, all right? Or maybe easier than classical mechanics some point. Now we have said all these things, all right? All these things. But in physics, right, if you look at physics, the main concern of physicists, as I said, is to predict the future. Okay, not only future, again it could also be past or the state at any other time. So the question is this: given the state, okay, at any one time, okay, how can we determine the state at any other time? This is the question that we are trying to answer, okay, or this is the question that physicists have been trying to answer all the time, okay. And in the case of Newtonian equation or Newton's equation, so in the case of Newton's equation, giving you the state at some time means you are given the initial position and initial momentum, right? Once these are given, how do you find the position and momentum at any other time? This is what you mean by state in classical mechanics. Okay? Let's say this is the state in classical mechanics. Okay? How do you find the state at any other time? You just use the equation F is equal to m d square x by dt square. Integrate it twice and use the integration constants, and you will get the state at any other time. Or we can simply get x of t and p of t. Okay? And this means this is the state at any time given x0 and p0. Right? The same thing can be asked in quantum mechanics. Right? Given the state, we said that states are represented by vectors. Given the state or the vector corresponding to a state at any time, what's the state at any other time? Or what's the equation that governs the evolution of the quantum mechanical state? And the answer is the famous Schrodinger equation. All right? It's the Schrodinger equation. It's the Schrodinger equation. All right? And again, there is no way of deriving this. Right? We can motivate that this can be the answer or something, but there is no way of deriving it, just like we cannot really derive Newton's equation. Right? So it's a fundamental, it's basically something fundamental. You have to take it as a postulate. All right? So this is the equation governing. This is the equation governing the time evolution of a quantum mechanical system. So given the state at any other time, what you need to do is that you solve this equation. You solve this differential equation, use the initial condition, and you can get the state at any other time, what we call as psi of t. Okay? It's another question whether we can actually solve this equation, because differential equations can get notoriously difficult to solve exactly, and we may have to use approximation methods, etc. And you see that there's an important thing sitting here. This is the Hamiltonian operator. This is the Hamiltonian operator. Okay, or the operator corresponding to energy. The operator corresponding to the observable energy. Okay. So you see that Hamiltonian operator somehow generates time evolution. Okay. The Hamiltonian operator has to do with the time evolution. The Hamiltonian operator determines the time evolution of the system. Okay. Or the Hamiltonian determines the time evolution of the system. We have seen also this in classical mechanics also. If you remember the Poisson bracket relations, etc., you will see that. Or if you look at the Hamilton's equations of motion, you know that Hamiltonian has something to do with time evolution. All right. So now solving a quantum mechanical problem means knowing the Hamiltonian. Right. Solving Newton's equation, knowing all the forces acting on the system. Right. If it is, for example, the gravitational force gmm by r square r cap or something. Right? Forgive this, we will write as r vector. Okay. So if you know the force, you can solve it. So in Newton's equation, what you need to know is the force acting on the system. In quantum mechanics, in order to solve the time evolution, to understand the time evolution of the system, to know how the state evolves in time, what you need to know is the Hamiltonian. So if you want to solve a problem, you have to know the Hamiltonian. Right? So you get the Hamiltonian from somewhere. What do you say? As someone might say, you beg, borrow, or steal the Hamiltonian. If you know the Hamiltonian, you can solve the Schrodinger equation. We'll see specific examples of this later on in our foundation course itself. We'll study a few small problems. All right. And as I said, we said that we can choose a particular basis, and then we can represent this by the corresponding expansion coefficients. All right. So if you represent this by the corresponding expansion coefficients in position basis or coordinate basis, then these are simply, we can also write it for IH cross dou psi of x by dou t, right, is equal to h psi of x. This is the usual Schrodinger equation that we might be familiar with from our undergraduate years. Okay. So I think I have covered the conceptual framework of quantum mechanics without really going really deep into the mathematical framework. Right? This is how it works. Okay. And while teaching, sometimes it's easier to understand to teach in a slightly non-linear manner. Right? You give you the complete idea first, and then we'll go into the specific details. Okay? There are a lot of mathematical details we need to cover regarding Hermitian operators, their properties, and eigenvalue equation, how do we solve eigenvalue equations, etc. Right? But assuming that this mathematical framework is there, perfect, this is the mathematical framework of quantum mechanics. All right? Okay, I hope these things are clear now. Now, we can do a problem here. Okay, let's do a problem. These kinds of problems are asked in competitors. This is a very easy problem. We can solve it with our knowledge. All right, just forget this term right now. Don't worry about it. We'll explain what this is. All right. Okay, so you can just imagine this our basis set. So consider a system whose state is given in terms of a set of basis vectors. All right, read it as basis vectors. Okay, orthonormality we'll discuss soon. We have to define inner product. So the given state, the given system is given. Sorry, the system is written. Okay, consider a system whose state is given in terms of these three vectors: phi 1, phi 2, phi 3. Okay. All right. What is the probability of finding the state in the system? All right, finding the system in the state phi 1. That means, as I said, this could be the eigenvector of any operator. Okay, it could be the eigenvector of the Hamiltonian operator, for example. All right. So once you suppose these are the eigenvectors of the Hamiltonian, once you measure the energy, right, the state of the system changes from psi to phi 1 or phi 2 or phi 3. All right, because once you make a measurement, you can never see it in superposition. You will either see it in phi 1 or in phi 2 or in phi 3. Okay, and what are the probabilities for this? The probability of finding the system in the state phi 1 is given. It can be calculated from this expansion coefficient. The probability that after the measurement this psi reduces to phi 2 can be calculated from this expansion coefficient, and the probability that the system reduces or the state reduces to phi 3 can be calculated from this expansion coefficient. Okay, that's the basic idea. Okay. All right. Now first we have to check whether this is normalized. So we have got C1 here, C2 here, C3 here, and it's a simple problem. These are all real. Right. So you check first mod C1 square plus modulus of C2 square plus modulus of C3 square. You see that this is equal to, if you square it, you see that this is equal to 3 by 9 plus 4 by 9 plus 2 by 9. Okay, and this is 9 by 9 equal to 1. So this is normalized. This is normalized. Okay, so the total probability adds up to 1. Fine, we don't have to do anything. Right. So the question: what's the probability of finding the state in finding the system in state phi 1? It's modulus of C1 square. Okay, so that would be 3 by 9 or 1 by 3. Okay, so this is the correct answer. Now if you are asked what's the probability of finding the state in phi 2 after making the measurement of the corresponding observable, right, of the corresponding eigenvalue, then the probability would be 4 divided by 9. Okay, that's given here. If the question was about phi 3, all right, what's the measurement, what's the probability of measuring the state, or what's the probability that after the measurement the state of the system is phi 3, you're given by phi 3, then it is 2 divided by 9, just the square of this. Okay, but the question was probability of finding a state in the state phi 1 or system in the state phi 1. Okay. Now you can imagine that these phi 1, phi 2, phi 3 are eigenvectors of the Hamiltonian operator. Okay. In that case, you are asking about a measurement of energy. Phi 1, phi 2, phi 3, for example, are the eigenvectors of the Hamiltonian. You are actually asking the probabilities of measuring different energies. Right? If the state is if the system after measurement is in the state phi 1, that means that the measured value of energy is simply E1. The measured value of the energy is E1. If this phi 1, phi 2, phi 3 are eigenvectors of the Hamiltonian operator. We don't know that, it's not given, but I'm just explaining it. Okay. Now such problems can easily be solved with the conceptual idea that we have got so far. We could do another problem here. Consider a system whose state is given in terms of a complete set of 5 basis vectors. Okay. We have got phi 1, phi 2, phi 3, phi 4 and phi 5. Phi 5. We have got a 5-dimensional space here. We have got a 5-dimensional space. Alright. As follows. Psi is equal to, this is the state. Okay. It's the linear combination of 5 states. It's a superposition of 5 states. Superposition of 5 states. All right. So in the way that we chose, in the language that we chose from the beginning, okay, it means that this electron, if we are talking about an electron, is in all these states at the same time. Right. This is the language that we chose. All right. That language itself is not forced upon, only this mathematics is forced upon us, but we chose to take it literally. I said I am following a literal interpretation. All right. So this means in the language that we chose to in the beginning, this means that the system is in all these states at the same time, just like we said the system, the electron is in both slits at the same time. Okay, so this is superposition. Okay, and it's given phi n are the eigenstates to the system's Hamiltonian. H cap phi n is equal to n epsilon 0 phi n. Alright, so the Eigenvalue equation is given, and they have given us a rule to calculate the eigenvalues. Okay, and this n, we assume this n corresponds to this. This is n equal to 1 here for this state, n equal to 2, this for this n equal to 3, and for this n equal to 4, and n equal to 5. Okay, so this means that, for example, h cap phi 1 is equal to 1 epsilon 0 phi 1. All right, h cap phi 5 is equal to 5 epsilon 0 phi 5. Okay, this is what we have. The eigenvalue equations are given. Okay, now we know the eigenvalues. What's the question? Right, n equal to 1, 2, 3, 4, 5, where epsilon 0 has the dimensions of energy. If energy is measured on a large number of identical systems, so we prepare so many systems, right, so many systems in exactly the same state. We prepare so many electrons. Let's say these are electrons. We prepare so many electrons in exactly this state. Okay, and on each of this electron or each of the system, you are measuring the energy. You are measuring the energy of each of this system. Okay, each of the systems. That's the question. If the energy is measured on a large number of identical systems that are all initially in the same state, psi, they are all in the same state, what values would one obtain and with what probabilities? Okay, find the average energy of one such system. Right? So let's see if we can solve this problem using the conceptual knowledge that we have already acquired. Okay, now this is the question. What values would one obtain? All right, so we are making thousands of systems exactly in this manner. Okay, why do we make identical systems? Why do we make so many systems? Because once you measure the energy, the state changes. Right, the state changes. Then again, you cannot measure the energy. We have got a different state. Right, so in order to find the average energy experimentally, what you have to do is that you have to prepare so many systems in the state psi. And first you measure this, then you have to discard it because the state has changed. Then you measure the energy of this, then discard that, then you measure the energy of this one. All right. So that's what we mean by identical systems. All right. Okay. What values would one obtain and with what probabilities? What are the values that one would obtain? We know that the measured values, the values that we obtain are measured values are eigenvalues. Okay, and what are the values that we are supposed to get? We will either get 1 epsilon 0 corresponding to the eigenvalue for phi 1. So it could be epsilon 0 or 2 epsilon 0 or 3 epsilon 0, 4 epsilon 0 or 5 epsilon 0. Alright. Okay. So these are the values that you will obtain. Okay. Sometimes you will get a number of times you will get epsilon 0, some other number of times you will get 2 epsilon 0, 3 epsilon 0, 4 epsilon 0, 5 epsilon 0. So if you measure the energy of this state, right, of this system or the system in this state, you will get either epsilon 0 or 2 epsilon 0, 3, one of this, right, one of this. Okay, so these are the values that you will obtain. On a single measurement, you will get one of this, all right. Okay. And with what probabilities? Okay, with what probabilities? So the question is again, what's the probability that you will get energy epsilon 0? Alright, so this is the question. What is P of epsilon 0? What's the probability that you will get epsilon 0? We know that this is proportional to, this is 1 epsilon 0, right? So that you don't confuse. We know that it's proportional to this expansion coefficient of the eigenvector corresponding to 1 epsilon 0. Am I right? So we know it is proportional to 1 divided by 19. Okay. Now, in order to make this proportionality into equality, we need to make sure that this is normalized. If it's not normalized, you have to normalize. Okay. So if you look at this, you just square these terms and add. Okay. You just square these terms and add. Okay. So modulus of C1 square plus modulus of C2 square, modulus of C3 square plus C4 square plus C5 square. Okay, you calculate this, and what do you get? This is equal to 1 by 19 plus 4 by 19 plus 2 by 19, okay, plus 3 by 19 plus 5 by 19. Okay, just square and add all this. What do you get? 15 by 19. Alright, this is not equal to 1, not equal to 1. So we see that the state, given state, is not normalized, Now how do you normalize? You just divide each of the coefficient by 15 by 19, right? You divide C1 by 15 by 19, C2 by 15 by 19, all this by 15 by 19, and you will get the correct normalized probabilities. Okay, because if you divide this by 15 by 19, etc., and you square and add, again you will get 1. Right? That's what you mean by normalizing. Okay. So that's what we have written here. This is, you can call this as the normalization constant. You can call this as the normalization constant. So you square and add all the coefficients, you get 15 divided by 19. Right? And as I said, possible energies are eigenvalues n epsilon 0, that is 1 epsilon 0, 2 epsilon 0, 3 epsilon 0, and 4 epsilon 0 and 5 epsilon 0. These are the probabilities. You get modulus of C square divided by A. So what's the probability of obtaining energy 1 epsilon 0? It is modulus of C1 square. Let me write it here. Alright. I don't have it here, but alright. So what's the probability of obtaining energy 1 epsilon 0? That's equal to mod C1 square divided by A. Normalization constant. Alright. And what's mod C1 square? Mod C1 square is 1 by 19. So that is 1 divided by 19 divided by or multiplied by 19 by 15. Okay, so that's equal to 1 by 15. Okay. So unless I have made a numerical error, this is how you do it. Okay. So instead of dividing, I have multiplied by the reciprocal. So the probability of measuring energy epsilon 0 is 1 by 15. Okay. Similarly, what's the probability of measuring energy value 2 epsilon 0? It's equal to modulus C2 square. Sorry, modulus of C2 square. Let's write it like this. The probability of measuring P of E, let's say probability of measuring 2 epsilon 0. Okay. That's equal to, let's say the square of this is 4 by 19 divided by the normalization constant, that's 19 by 15. Alright. So that's equal to 4 divided by 15. Okay, these are the probabilities. Okay. Similarly, you can calculate for all of this. Right. So what's the probability of measuring 3 epsilon 0? That would be, I think we should write it down. Right. Alright, no problem. Okay, so that would be 4 by, this for this it's 4 by 15, here it would be 3 by 15, and for this it would be 5 by 15, which is equal to 1 by 3. Okay. I hope that's clear. That's how we calculate the probabilities. Alright. Now find the average energy of one such system. Okay, so what do we mean? What do we mean when we say that the probability of measuring energy epsilon 0? Okay, what do we mean when we say that probability of measuring energy epsilon 0 is 1 by 15? What do we mean? This means that 1 out of 15 times the energy measured would be epsilon 0. Right? Which means that if you make a large number of measurements on identical systems, you cannot make the measurements on the same system because the state changes. But if you make a large number of measurements, 1/15 of them, 1/15 of the outcome would be 1 epsilon 0. Okay, and 4/15 of the outcome would be, or 4 divided by 15 of the total number of measurements, you will get 2 epsilons over etc. That's what we mean by probabilities. Okay. Now there's another question. Find the, I hope this is clear. Okay. Find the average energy of one such system. What's the average energy? Now how do you calculate average energy? How do you calculate average energy? Okay. How do you calculate average energy? Let's say, so suppose you are making these measurements, you have done experiments in your laboratories, right? So let's say that n times you get E1, n1 times you get energy E1. Okay, what do you do in your laboratory? You add all the values and divide by the total number of measurements. Am I right? So in your laboratories, what you do when you make a measurement, or you need to take an average, what you do is that you will add all the values that you got, E1, E2, E3, etc. Okay, add all the values that you got and divide it by the total number of trials that you have made, or total number of times you have made the measurement. Okay, so you get n1 times energy E1. Right, so you have to add all this up, and let's say n2 times energy E2 and n3 times energy E3. Okay, n4 times energy E4 and n5 times energy E5. Alright, so you make a large number of measurements on different systems identically prepared. Okay, and what do you get? You get n1 times E1, n2 times E2, n3 times E3 and n4 times E4, n5 times E5. Right? What do you do now? You add all this up, you get the total number and divide it by the total number of trials. Alright, in this case it is n1 plus n2 plus n3 plus n4 plus n5. Okay, or this you can write as a total number of measurements, capital N. Alright, now this you can again write it as n1 by n E1 plus n2 by n E2 plus etc. And what is this n1 by n E1? This is exactly what this is exactly the measured probability, P of E1. Alright, you can write as P of E1. So this is equal to P of E1 E1 plus P of E2 E2 plus probability of measuring E3 E3. This is what we mean by average value, average energy. Okay, and now we already know how to calculate these probabilities. We know how to calculate these probabilities from theory. Right, so the average value obtained can be predicted by our theory because P of E1 is given by modulus of C1 square divided by A. P of E2 is given by modulus of C2 square divided by E, etc. Okay, modulus of C2 square divided by A, etc. Okay, so you can calculate the average energy like this. You just multiply each value of energy by the corresponding probability. Okay, in other words, you can calculate it, you can do it at home. Right, you can do the numerical calculation, but the answer would be this. It would be modulus of C1 square divided by A multiplied by, let's say, epsilon 0. Right, it was 1 epsilon 0 plus modulus of C2 square divided by A 2 epsilon 0 plus modulus of C3 square divided by A 3 epsilon 0. Okay, plus modulus of C4 square divided by A 4 epsilon 0 plus modulus of C5 square divided by A and 5 epsilon 0. This would be the average energy. This average energy is also called the expectation value of the energy. Expectation value of energy. Alright, that's this is the expectation value of the Hamiltonian, for example. Alright, so average energy is the same thing that we call as the expectation value in quantum mechanics. Alright, so expectation value, the term expectation value may be a bit confusing because it's not the expected value. Expected value is the value with maximum probability. Right, it's not the expected value but the average value. By expectation value we mean the average value. Okay. I think this is clear. You can do the numerical calculation at home. Okay, all right. Now, so we have just looked at the conceptual framework. We know how quantum mechanics predicts the probabilities. We know the rules. So we know the rules to calculate the probabilities. We know the rules to make predictions. All right, and we just use it in this manner. Okay. Alright, there are many more problems that we can solve later on. Okay. Now, I'll just stop by talking about a dual vector space. okay, because someone had asked about dual vector space, I think yesterday, right? So first we'll go to simplest concept about what do you mean by a dual, right? So if you take a complex number, z is equal to x plus iy, you know that you can also represent it in a polar representation. It's written as r e raised to I theta, where theta is this angle, okay? This length is r, and this is r cos theta, this is r sin theta, okay? So r cos theta is x and r sin theta is y, okay? So it's x plus iy, and you know that r cos theta plus ir sin theta can be written as r e raised to I theta. So complex number can be represented like this also. Now we know that every complex number z has a complex conjugate that we usually denote by z star, right? Every complex number has a complex conjugate, and we know that multiplying a complex number and its complex conjugate, okay, this is what we call as modulus of z square, okay, you get a positive result, r square. We know these things, and it's convenient to call z and z star as dual number systems. Dual number system. By dual we just mean this: corresponding to every z there is a unique z star, right? Corresponding to every z you have a complex space. Corresponding to every z you have a z star. Okay, you can call this as a dual number system, or dual. Yeah, you can call it as a dual number system. We can say that z star is the dual of z. All right, and you see that this dual is needed. The dual is needed to get a real number out of it. All right, you get a real number using the dual. Okay. Okay. In much the similar manner, similarly, you can talk about vector space and a dual vector space. We usually call it as Ketz and Brass. Okay, this is in Dirac's notation. So just as complex numbers have dual version, there is a dual version to vectors also. Okay, you can think of it as the complex conjugate vector space. Okay, don't get fooled by this term. It's some other kind of vector space. Okay. So corresponding to every ket vector, just like corresponding to every complex number, you have a complex conjugate. Corresponding to every ket vector, this usual vector we call it as a ket vector. Okay, if I didn't introduce that terminology, okay. There exists a bra vector. Okay, there exists a bra vector which is denoted like this. Okay, so the space of this bra vector, so this is unique, the correspondent is unique. Corresponding to every vector there is a bra vector. Okay, and the space of this bra vectors is known as a dual space. Now which one you want to call dual space is just a matter of convention. We call this as the vector space and this as the dual vector space. Alright, we usually call the space of Ketz as the vector space and the space of Brass as the dual space. Okay. The bra vectors also form a Hilbert space, or form the same axioms that are followed by Ket vectors. All right, bra vectors also form a linear vector space. Okay. Now the points to remember when you take this dual vector space is this. Okay. If bra A, this is usually called as bra A. Okay. If bra A and bra B are the bras corresponding to A and B, right? Ket A and Ket B, then so there is a linearity when you take this bra, right? So bra A plus bra B, this is the bra corresponding to A plus B. Okay, so if the bra corresponding to A is this and the bra corresponding to B is this, okay, then the bra corresponding to A plus B is simply A plus B. It's just like taking the complex conjugate, but it's not the complex conjugate. Another thing you want to remember is to remember that there is a complex conjugate. So if ZA, okay, if there is a number here, right, if ZA is the Ket vector, then the corresponding bra vector is not ZA, it is Z star A. Alright, so when you go from bra to Ket, there is an extra complex conjugation. Numbers have to be complex conjugate. Okay, we'll look at an example. We said that column vectors or column matrices form a linear vector space. So if A is given by alpha 1, alpha 2, alpha 3, alpha 4, it's a column vector. Okay. This is an example. We know that these column vectors all satisfy the axioms of being in a linear vector space. Then the corresponding bar vector is given by, you take the transpose of it, alpha 1 star. This is a row vector. Okay, alpha 1 star, alpha 2 star, we have written it here. Okay, this is a row vector.
It's not just a row vector, it's a row vector with each element complex conjugate. All right, it's a row vector with each element complex conjugate. Okay, now we'll use this what is a dual space in order to define an inner product, all right, or a scalar product. A scalar product means that you take a vector and you need to map it to a real number or a complex number or a scalar. Okay, you need to take a vector and map it to a scalar. For that we use the concept of inner product or scalar product. Okay, and we know in the usual three-dimensional vector space, if we have R vector, we can write R vector dot R vector like that. Okay, we know that. Or we have, let's say we have got two vectors. A vector is equal to AXI plus AYJ plus AZK. We'll do the corresponding thing in linear vector space in the next class, all right? And B vector is equal to let's say BXI plus BYJ plus BZK. We know that A dot B is, this is in three dimensional, right? This is AXBX plus AYBY plus AZBZ. Okay, so actually we are multiplying A vector by the corresponding dual here. Okay, this is a real vector space, so this is easy. We can write A vector, for example, as a column vector, AX, AY, AZ. Okay, and what's B vector? B vector is the column vector BX, BY, BZ. Right? So there is no way to get a scalar from two vectors. Okay, you need a dual space. Right? So if you need A vector dot B vector, what is A dot B in this case? It is, let's say, AX, BX, AX, AY, AZ multiplied in this manner, right? BX, BY, BZ. Okay, so this is a dual vector. This is a dual vector, right? We can say this is the ket, this is the bra corresponding to vector A. If you like this notation, you can say this is the bra corresponding. So we always need a dual vector in order to map a vector to a scalar. Without that you cannot do it. You cannot simply multiply two vectors. You need a dual vector. Okay? That's the reason we have introduced a dual vector here. We will be defining the inner product. Okay, we will be using the inner product or the generalization of this scalar product in the case of Hilbert spaces. All right, the scalar products are really important. Okay, so we'll have to look at it in the next class. I'll give you the basic idea. Scalar product is represented like this. Okay, the scalar product is represented like this. It's known as a bracket. It's known as a bracket. Okay, this is the ingenious notation of Dirac. Right, he took a bracket and split it into bra and ket. Right, this is a bra and this is a ket, and together we have a bracket and it's a scalar. The scalar means it's generally complex. All right, it's generally complex. And we'll look at the properties that needs to be satisfied by an inner product. Okay, that's given here, and we'll start discussing this in the next class. All right. Thank you. And if there are any questions, or if you want to involve in a discussion, the link will be given in the comment box. Please join in a Google Meet. Okay. Thank you. I hope you enjoyed the lecture.